My name is Tamás, and I am a PhD student at the Technical University of Delft, and I also... Really? How about now? Okay. That's the best I can do. Maybe speak a bit louder.
All right, so Tamás is a PhD student at the Technical University of Delft. And I happen to have the opportunity of supervising him there. He's also working in a software company called Itemis. And this is work we've been doing together in the last couple of years. And so this talk is really about program analysis and how to incrementalize it. And basically, as a starting point, most software development tools really use program analysis or information computed by program analysis one way or another. And so let's look at a couple of examples. I need to mirror the screen again. So this is a simple Java program where the program analysis you might want to run, you can probably not read the error message very well. It says recursive class inheritance detected. So it's a very simple analysis, right, where we basically check the structure and find cyclic inheritance chains. Another example that you might care about is when you have a little bit of a complicated piece of code and you want to generate a control flow graph that you can use for further analysis. So for example, we can use a control flow graph like this with read and write information of variables to do an uninitialized read analysis. All right, so in this example, var1 is not initialized to proper value. And when accessing it down there, we want to get an error message. And all of these analyses, we want incremental. So as the developer changes the code, we need to be able to update the error messages that are computed by our analyses. If you fail to deliver this kind of feedback in time, developers will stop trusting the analysis result. They will have to wait and like there needs to be like a gear moving somewhere, right? And they have to wait until the gear stops moving. Really want these analyses to run fast and provide this feedback immediately. Last example we have is a bounce to analysis, a bounce checker, right? So here we have an array which is initialized towards the top of size 10. And then somewhere in the code, we do an addition where we increase the index by 10, but only in the else part. Sometimes we do that. Then when we try to access the array at index, this is potentially out of bounds. We need to get this kind of error. So there's a whole range of analyses with different levels of sophistication. And for all of those, we want analysis feedback to be computed immediately. And the way that we do this is to incrementalize the analysis. So the basic idea is this. In the very beginning, you have some source code on the left-hand side. What we want to get out is some feedback about that code on the right-hand side. If you don't have an incremental analysis, you're going to basically have the same amount of time after every change. So what we want to do at a high level is to incrementalize it so that whenever there's a change to the source code, we don't actually process the source code. What we do is we process the change made to the source code. And this is going to give us a much shorter incremental run for the analysis. And we're going to update the old feedback. We're going to retain that feedback that hasn't been affected by the change. And we're going to update, rewrite the analysis information that is affected by the change. And we can do that multiple times, right? And every time we get this incremental benefit. And in theory, this kind of approach, this kind of incrementalization can give you asymptotical performance improvements. And in practice, we have observed speedups between 10 and 10,000 fold. So this can give you significant speedups. All right, so what we do in our work is we build a framework for incremental static analysis, right? I showed you that whole range of analyses that we want to support. And this framework is supposed to allow you to express those and provide that incrementality automatically. Because making analyses incremental is, if you do it yourself, is very labor intensive and very error prone because you have to do a lot of tracking to figure out what information is affected by what information in the program. All right, so the agenda roughly for this talk is to talk about 4 things. We want to talk about how we represent programs in a way that allows us to do incremental analysis. Then we discuss a simpler form of analysis, which we call relational analysis first. And then we discuss about more sophisticated analysis and how to integrate that into an IDE. All right, so what's the basic idea? The basic idea is to represent programs as relations in a database, specifically in a deductive database. So who of you has heard of data log? Can you raise your hand? All right, that's a good share. Nice. So we really follow a data log kind of approach, but then extend it. So let's take a look at a simple example. So this is a simple program in your favorite language. It has 5 statements, an assignment, an if statement with an else branch, and then another method invocation. And we can represent this as a relational, as a set of relations. And basically, the key idea that we follow is that every node in the AST becomes a relation, and then the entries of these relations are all the nodes belonging to that kind of node. So for example, our program has 5 statements, so our statement relation has 5 entries. Each of those is really a reference to the AST node. We have 3 assignments in our program, so we have a relation that identifies these 3 assignments. We have 1 if statement, and then besides this kind of node information, we also have structural information, like the next and the parent relation, and these really capture the structure of the AST. So for example, the relation next, it captures things that are subsequent in the program. So statement 1 is followed by statement 2. Right? That's why we have a tuple 1, 2 in the next relation. Similarly, statement 2 is followed by statement 5. I mean, there's a whole bunch of stuff happening within statement 5, but immediately after statement 2, there's statement 5 in the control flow. Similarly, we have parent edges, right? So the parent of 3 is 2, and the parent of 4 is also 2. And we have this kind of information for all the things inside the AST. What can we do with that information? Well, we can write queries against this kind of database. And what these queries really compute is derived relations. A derived relation is any information that we compute about the program. The program is basically the facts that we take as input, and the queries compute information about that input. If we take the same program again, and then we can look at how would we define a control flow analysis, for example. How would we, or a control flow graph, I should say. So this is data log syntax. So actually, this is 3 rules for the same relation. We have 3 alternatives, and in fact, we have more alternatives, but we show 3 alternatives for control flow edges. So the first rule is pretty simple. We have a control flow edge from to whenever from is directly followed by to, and from is not an if statement or any other control structure that would affect the control flow. Right? So for example, in our program above, we have the first rule produces a pair 1, 2, because 1 is directly followed by 2, and 1 is an assignment and not an if statement. The second rule is a little bit more complicated. It basically describes the flow into a branch of an if statement. So if we have an if statement, then and first is contained in that branch, and first is actually also the first statement in that branch, then there is a flow from the branch head to the statement, the first statement in that in the body of that branch. And kind of similarly, the last rule describes the flow out of an if statement, right? So if last is indeed the last statement in that branch, then we have an edge from last to 2, where 2 is the thing that follows the if statement. So using these rules, we can compute control flow edges for the program above, right? So I already mentioned edge 1, 2, but we also have 2, 3, which is produced by the second rule, right? It's a flow into the if statement, into the if branch. We have 2, 4, which is also produced by that rule, flowing into the else branch. And then we have 2 edges flowing out of the branches, from 3 to 5 and from 4 to 5. All right, so this is a pretty simple example, but we can do more complicated things as well. For example, we can describe a points to analysis, which is a relation that relates, at the statement. The from is a variable, and to is what it points to at that place. For example, if the statement we're looking at doesn't do an assignment, so it does not assign to from, then what we do is we find the predecessor of our current statement and what it points to for from, and simply propagate that. The other rule says that if the statement does do assign to from, then, well, what we need to abstractly interpret the expression. It's not shown here, it's basically hidden inside this other relation, and figure out what it points to. So let's assume we use some labels for these two initializers here, O1 and O2, then the points to information we compute is this. At statement 3, right, which is the then branch, C points to O1. At statement 4, which is the else branch, C points to O2. And then after the if statement at statement 5, C can point to either O1 or O2. So both of those get propagated. All right, so this was basically a primer into doing data flow analysis with data log, but how to incrementalize that. And this is what this talk's really about. The key idea is that incrementalization corresponds to change propagation, right? As I showed in this overview slide, we really want to propagate the changes. We don't want to reanalyze the entire code. So let's say we do a simple change to this program. We insert an else if branch in the middle. Well, what we want is we want to update the control flow graph, right? So we want to remove the flow from 2 to 4, right? Why is that? Well, because every flow from the if condition needs to go to the else if condition before it can go to the else branch. So we remove 2, 4 and we insert 6, 4, where 6 is the condition of the else if branch. It also affects the points to information, right? So if we use labels again, then we get an additional possibility for what C might point to at statement 5. Right? So in this new branch, C points to O3, and then after this if statement is complete, it points to O1, 2, or 3. So this is basically what we want. This is the specification of what the incremental analysis needs to produce. It needs to produce these kind of deletions and insertions. But how can we do that? And this is where I give over the word to you.
So let's give it another try. So in our work, we use a computation network to essentially translate the analysis that you have seen before. And this network has two kinds of nodes. First, these gray ones, these are what we call input nodes. They enumerate the information from the analyzed program, from the AST. And what Sebastian said with the next relationship, the parentship, and so on, all those relations are here with their tuples. The key thing is that these nodes in the computation network, they perform caching, so they cache their tuples, and whenever something changes in the program, then they can efficiently reply to that changes and what happens then in the dependent nodes. So here you see now computation nodes. This is the other kind of node for all the various parts of the analysis that you saw before, container statement, container branch, and so on. And finally, we have here the C flow, which is the interesting relation that encodes the control flow edges. Now, when the change happens, the change first manifests in the input nodes. So there we have now new tuples inserted or deleted. And then the nodes essentially propagate the delta on their outgoing edges to the dependent nodes. In response to that, the dependent nodes can also update the contents. And they can also propagate only the delta on the outgoing edges. And this way, here we can see that Cflow now has the 4 new tuples and then one lost control flow edge. So this is how the analysis result changes. Now, in our work, we have built a complete framework for incremental static analysis. And this is something that we call Inca. Inca comes in the front end with a data log like DSL that you can use to define the program analysis. It uses the computation network under the hood. So we take this declarative specification of the analysis and we translate it down to this computation network. And the language and the runtime system of Inca is independent entirely of the analyzed language, so you can use it for any subject language you want. I would like to say a few words about the evaluation. So we have implemented various analysis for various languages with Inca. There are 3 code bases here. The first one is Smart Meter, which is a commercial project. This is doing automatic billing for electricity consumption. Second one is Embedder Importer. This is a commercial project. Toyota ITC, this is a benchmark for static analysis tools. You can see here their sizes. So the size is up to 44,000 lines of code, and they are either implemented in C with some language extensions, Java, or purely C. We have implemented 3 analyses for these 3 subject code bases. For example, we implemented well-formatedness checks for DSLs, we implemented findbugs rules with Inca, and we also implemented a points-to analysis for C. Here in this column, you can see the initialization time. This is the time that it takes to create the computation network under the hood. And this is essentially a non-incremental run. This is when we build up the caches. And then here you see the update column, which is essentially we introduce programmatic code changes into these subject programs, deleting statements, duplicating methods, all kinds of program changes. And then we measured how much time it takes to update the analysis result. And here you can see that they are in the ballpark of a few tens of milliseconds, which is exactly what we need in interactive applications. So compared to the non-incremental version of the analysis, we achieved a 2-3 orders of magnitude speed up.
Well, but hold on. So, I mean, there's a number of requirements for incremental analyses, and it feels like you only touched upon the first one, right? Immediate feedback and efficiency. But there's other ones. There's correctness. We want exactly the same result as a non-incremental analysis would have computed, right? So we don't want to be faster by doing approximation. We want to be precise, nonetheless. Then there's expressiveness. I've promised the audience before that we would do data flow analyses, but the ones that you showed, they were just, simple analyses, right? Because a data flow analysis it's not enough to relate program elements, right? You need lattices, and they need to be customizable. And it needs to be possible to generate lattice values and to aggregate over them. So how is that going to work?
Actually, that is a good point. So I can avoid talking about this, but. So let's take a look at another example then, an interval analysis. So an interval analysis uses interval lattice. I'm not going to go into a mathematical definition now about lattices, but I want to point out the key things here. So lattice has a bottom element and a top element. For the interval lattice, we are talking about integer ranges here. The bottom element is the empty interval. The top element is the -infinity plus infinity interval. In between, we have all these integer ranges. And what is important that there is a least upper bound operator and the greatest lower bound operator on lattices. So we can aggregate 2 lattices together, 2 lattice values. Now, the key thing is that a data flow analysis, apart from having derived relations, as Sebastian pointed out, also relies on lattices and recursive aggregation over lattices. So looking at this subject program, it is a very simple Java code which has a loop here. We have an interval analysis implementation that could look like this. So the key idea here that we use 2 data log rules that recursively depend on each other. We have an interval after and an interval before. The key thing is that interval after is abstractly interpreting the effect of an assignment, if there's any. So if the current statement, the current control flow location, kills the value of the variable, kills the interval that is associated to the variable, then we simply want to propagate the interval that was associated before the control flow location. Now, control flow before is doing the hard work because it uses a helper relation, the predecessor intervals, to collect all the intervals that are coming from control flow predecessors. And this is important because it may be the case that the control flow location is actually a control flow merge point. In this case, we want to aggregate the intervals together. And notice here that we are using the least upper bound operator to aggregate the interval lattice values that come in at that location. Now, we rely on the control flow analysis from before, so that looks very similar. I have highlighted here 2 edges because they represent essentially how we can go into and out from the loop. Now, let's take a look at the evaluation, how that one goes. So for X, we start with the 7-7 interval. This is when we interpret the statement 1. For Y, it's 0, 0. Then it gets propagated to the loop head and then to the loop body. And for example, at statement 5, we have now that X is from the interval 11, 11, and Y is from the interval 0, 1. That is because there is a ternary expression here at statement 5, which gives the interval 0, 1 to the Y variable. Now, an interesting thing happens here because this interval now gets propagated back to the loop head. So now at that point we have 0, 0, but now 0, 1 also comes in there, so we want to aggregate these values together. That becomes 0, 1. Now this gets propagated to the loop body and then again to the loop head, so we aggregate again and this becomes 0, 2, and so on. The key thing is that at some point we would like to apply some widening operator because we want to accelerate the fixed point computation. So this is essentially, for the sake of this simple example, we just want to do a big jump in the lattice and then jump to the top element. And this way we get the interval which is 0 plus infinity. Now, incrementalizing data flow analysis comes with a lot of challenges. So let's take a look at a simple example here where I'm replacing the initializer from 0 to -1. In response to that, I'm expecting that the 0, 0 interval gets deleted and the -1 gets inserted. Right? So an idea would be that we use this change propagation that we have seen before, where we propagated deleted and inserted tuples. So in response to that, the expected result is shown here. So we have now a new initial value at statement 1, and also the lower bounds are updated at each one of the other locations. Now let's take a look at another example where we delete the -1 and insert a ternary expression. In response to that, -1 gets deleted and -1, 0 gets inserted. This is now a bit trickier because the thing is that the lower bound is shared and somehow we want to reuse the previous analysis result. Instead of just blindly propagating the deletion of -1, -1, we actually want to reuse the previous result. And then this way, you can see here that only the statement 1, the interval there changes, but the rest remains the same. Now, a third change removes the ternary expression and then inserts back 0. In response to that, we delete the -1, 0 and insert 0, 0. Now, there is a key thing here, which we call a cyclic reinforcement. The problem is that when we want to propagate now this deletion and insertion and then evaluate it at the loop head, problem is that when we want to insert 0, 0, we also need to consider the interval that comes from the statement 5, right? Because that has an effect on the loop body. It is propagated back there. Even though this -1, 0, we actually got there through a series of iterations from the initial value. But the analysis needs to consider that. And the problem is that when we want to apply the least upper bound on 0, 0 and -1 infinity, it yields -1 infinity. And note that this is the wrong result. This is not what we want. So the problem is that cyclic reinforcements can result in either wrong results or, in the worst case, non-terminating analysis. So I'm not going to show the non-terminating case here, but you could play around with this analysis and then see for yourself this can actually happen. Let's take a closer look at this loop head and what happens there. So we had initially this 0, 0 interval. Then the 1, 1 got inserted. We applied the least upper bound operator, so it became 0 and 1. And then we issued a deletion and an insertion. But the key thing is that this deletion here, this shouldn't be handled in isolation, because what is a key point here is that actually this one here is less or equal than the interval that we are just about to insert. And together they represent something that we call an increasing replacement. So from intuitively what this means that even though we delete an interval, we immediately insert an interval that contains the deleted one. And this way we can essentially treat them together instead of separately handling them. And this way we can avoid the cyclic reinforcement and then this wrong result or even the non-termination. And recognizing increasing replacements at runtime is key to our solution, and this is how we can fix this problem. Now, let's take a look at the evaluation again, now with the extended framework that also supports lattices. So we also implemented a strong update points to analysis, which is like a special kind of points to analysis that gives up on precision in certain cases. We evaluated it on 4 Java code bases. These are popular repositories that we simply cloned from GitHub, and they are in the ballpark of, their sizes are up to 70,000 lines of code. You can see here that the initialization time now is bigger than before because now we have like a more complicated data flow analysis that relies on lattices. The initialization time is up to a minute, but then we still keep the fast update time. So this is still in the ballpark of several milliseconds. Another case study that we also did was we implemented string analysis. These string analysis are keeping track of the longest common prefix, longest common suffix, and the contained characters of string type variables. So what we varied here is actually the data flow property, like how many data flow properties we keep track of. The code base was the same. This is the largest code base, our subject code base, the Berkeley DB. And then we changed the number of data flow properties. You can see here how it affects the initialization time. So for example, in the worst case, this is now 20 seconds, the initialization time. And then we still have really fast update times, which is exactly what we need for the interactive applications. I just want to lay out all these components into the framework as a closing remark. So you can imagine this whole framework. Here's a software engineer who's working in an IDE. We expect that the IDE translates the program changes into AST changes, node deletions, edge insertions, and so on. This is our analyzed program. Here's the Inca analysis code, which is developed by an analysis developer, which is through the compiler translated to this computation network and the underlying algorithm, which we call DRED-L. Now, this is entirely independent of the subject language and of the IDE that you are using. Because of that, it has this navigator component, which is essentially just an adapter pattern, letting this evaluation engine know how the AST is represented in the IDE. This component here initializes and, most importantly, incrementally maintains the analysis result, which then can be used to provide feedback in the IDE. I'm going to skip here a slide and simply conclude here. So we used Inca. Essentially, this is the timeline of Inca. We started here with relational analysis, and we used that to develop fine-bug rules, for example, and control flow analysis for C. You can see here the speedups that we have achieved. So this is in the ballpark of 2 orders of magnitudes. And then we extended Inca with support for lattices and recursive aggregation over lattices. And then we used this extended framework to develop type checkers for featherweight Java, for example, and data flow analysis for Rust, and also data flow analysis for Java, like the strong update points analysis that you have seen in this presentation. I want to emphasize that Inca is an open source framework, so feel free to give it a try. And we have also a bunch of papers on Inca. The various aspects are documented. Thank you for your attention.
Okay, then questions, please.
Hi, Klaas van Schelven. So I have a question now about your motivation. I'm wondering if you're not underselling the motivation, because you're only talking about increases in speed. But in my mind, the most interesting part about incremental static analysis is about being able to pinpoint a particular program change, because usually when you're doing static analysis, you're looking for something that's wrong in your mind or something that's interesting in your mind. And what is more interesting than finding out when that interesting situation came into being? So I'm wondering, A, is this part of your motivation? And B, are you able to somehow get that kind of information in some structured form out of your IDE and present it to your user such that they may be able to use that information?
Would you like to answer? Should I answer? Yeah.
Oh, sorry.
I gave up the microphone. All right, so this is an excellent question. We haven't thought so much about using this to figure out when the error occurred, when the bug was introduced. But really, I think it really fits well with our motivation, which is to continuously provide feedback, right? So whenever you make the smallest change, you immediately get feedback about, especially the non-local effect of your change, right? And I think that this very well aligns with what you suggest. So thank you very much for this.
Hello. Could you go back to your slide about dealing with reinforcements? Because it seems like you're saying that your strategy is to identify increasing changes, which you can handle well, but what if the change isn't increasing?
Well, so if the change is not an increasing replacement, then we can't do any better than just simply like pruning the old result and then rederiving the new one. So for that case, we don't know any better at this point.
So you sort of rerun the fixed point
Yes.
until it converges
Yes.
again? Okay.
Then we handle the deletion and the insertion separately.
Okay. You might want to look at differential data flow, which has a
I
strategy for...
I have that on my radar, but
Okay.
thank you.
Questions?
Yeah. Yeah.
Thank you. So, other than the lattice results, the very last result you presented, the incrementalization of the data log part, what's different there? Is there something different from what a regular data log engine would do? Because I couldn't see something that would be different. You say you invalidate, for instance, in negative results, but how much do you invalidate? Do you have some clever algorithm? How much provenance do you keep? What do you prune? What do you recompute? Because every data log engine does this. So up until your UPSL 18 paper, the lattice-based stuff, all the previous stuff is kind of standard for data log engines, right?
Yeah, so that part, like incrementalizing the relational analysis, you're right. So actually under the hood, we have this DRED algorithm, which is the delete and rederive with some special optimizations. Like the optimization you asked, we are keeping track of support counts for tuples incrementally so that we actually know how many derivations are there for a tuple. And then this is how we can efficiently handle deletions. And if your question was about like what is new, for example, in the ASC paper, because there was an ASC paper about Inca, then the key thing was that we implemented this whole thing in a framework and we actually analyzed the analysis code to try to be clever about incrementalization. So there is a meta-analysis running on the analysis to figure out like what kind of program changes cannot affect the analysis result at all, because then they don't even need to enter the computation network.
Hi, Joost Vroog from Mendix. Can you use the information that's inside the framework to suggest how to resolve an issue that was suggested? Because you know all the nodes where it comes from. Could you help users there?
So I guess this is about like traceability, tracing back to the source program in some way. Well, that's a good question. I'm not sure how to answer this. I didn't really think about this. Yeah.
So one of the slides, pretty much in the beginning, maybe your 10th slide or so, you have these tables, and I wonder how exposable are these tables to your user and how
Like
much
these
sense?
ones?
Yeah, these ones. So this is basically, if this was understandable for users, like in non-trivial examples, I don't know if it is, but if it is understandable for users, this is the traceability, right?
Yeah, I mean, you could like programmatically recover the trace how you probably got to a tuple. So probably it would be possible. I mean, all the information is there. Currently, we don't have something like this.
Actually, there's a slide where there's like red also.
This was the incrementalization. Yeah.
I mean, one thing about these tables is that they can serve as the basis for a lot of feedback being produced from that, right? So we haven't really looked into how to produce the best possible feedback, and let alone, I mean, what you suggested before, to use the changes as something that affects the feedback you give, right? So that you talk about changes in the feedback itself, rather than really just updating the feedback as. So what we really looked for so far was that notion of correctness we talked about earlier, where the incremental analysis produced exactly the same feedback as if it was a non-incremental analysis run. So I think it's a very interesting suggestion.
Eric Bodden, hi. So in your evaluation, were any of the analysis that you implemented interprocedural?
No,
Okay.
we haven't yet covered interprocedural analysis.
Okay.
This is something that we are experimenting with nowadays.
But then aren't intraprocedural ones fast enough anyways, so that you don't really need incrementalization?
Well, I mean, we have already evaluated these analyses with other frameworks, and that was not our experience.
Okay. Thanks.
More questions? Maybe I have a question. What kind of analysis you cannot handle, you think? Because you showed points to analysis, you showed type checker, it seemed like various applications. Is there any specific thing that is hard for this framework?
So currently what is a missing feature, and we know already from the experiments with type checkers, is that we cannot support collections. So it's not possible to iterate over a certain number of things. I mean, of course, the lattice operations currently in our framework, they're implemented in pure Java. So there you could kind of hack the system by leaving the declarative word and then doing it in Java. But currently there's no way to iterate over a collection in the DSL. And this is a missing feature. We already identified this, that this would be very helpful in many situations. So this is just one example.
Yeah, thanks.
Okay, there are no more questions, and let's thank the speakers once more.
So there is a coffee break, and the next session starts